us for the special seminar today. It is my huge honor to welcome Professor Shi-Kwang Lee of the College of William & Mary. And Professor Lee is a world-class and expert in matrix analysis and also in combinatorics and quantum computing. And he is the first professor of mathematics at the College of William & Mary. He's got his PhD from the University of Hong Kong in 1986. He has numerous honors, far too numerous to enumerate. So
take the red dot.
Yeah. So there we go. So without further ado, Professor Shi-Kwang Lee, some matrix problems results in quantum information science, and I'll pass off the floor.
Thank you. Thank you very much for the nice introduction. I didn't bring my quantum computer. It caused all this trouble, so next time I will use it. So, as introduced, I'm Shi-Kwang Lee from College of William & Mary, and also because of my recent interest in quantum information science. So I joined the Institute for Quantum Computing in Waterloo, and just spent actually 2 months there. So this year I'm in research leave, so I have more chance to interact with people there. So any physics student in the audience? Okay, so I pretend I'm the physicist here to explain to you what is quantum mechanics or quantum computing. But don't worry, so no quantum mechanics is required in this talk. I have some accent, so everyone can hear me clearly. Okay, if I get too excited, I may speak very fast, even let my Chinese come out, so stop me at that time. Okay, so let me give you a picture showing what is the basic quantum computing model people trying to work on. So in the future, they want, for various reasons, they believe that they, for example, there's some limitation for the current conventional computing device, and also there is getting things smaller and smaller. One tiny chip have to accommodate all this network on it, and unavoidably it will hit quantum effect. So many reasons, people think that maybe in the future we need to have some quantum computing device. So the idea is very simple. You can compare with the conventional computing device. We use mathematically 0-1 sequences to be your input. You are talking about picture, you are talking about English, you are talking about mathematics. It doesn't matter. All encode in 0-1 sequence. Using Boolean algebra, deterministic model, instruct the computer to how to manipulate 0-1 sequence to achieve your job of computing, spell check, handling data in any kinds, pictures, and so forth. Same idea. You need something to help you to store and process information. In this case, quantum computing use quantum state. And instead of binary bit, they call it quantum bit. So the shorthand, the abbreviation is qubit. So qubit is the two-dimensional object, which is like our photon. Photon have two measurable states, so the quantum system describing the photon action is actually a two-dimensional Hilbert space. And the simplest types of quantum system you can imagine, when you stack them, it will help you to store and process information. And then there will be a black box. So depending on what kinds of physical system would allow you to implement or exhibit, they first of all have to exhibit quantum mechanical behavior. So there are optics, it can be NMR, subparticle anyons. So people are still fighting on what kinds of system is the best, allow you to manipulate the system to achieve your job is storing, transmitting, and processing information. And then after you prepare your quantum state, put it in this quantum environment, let it evolve according to quantum mechanical rules. And then you will do some measurement and try to extract information. Okay, so roughly it is like that. So you have to design some quantum algorithm so that you can use the quantum bit property to help you to sort out something which are useful. Just like you want to go to Google, you search a word, you find a lot of information, you want to extract useful information. Number one, you have to have a computer to do your setup. Number two, you put in the right keyword. Number three, tons of information come out, you have to do the correct measurement. In particular, in quantum physics, even doing the measurement would be very tricky. We know that if you do a measurement on the quantum state, it will destroy the quantum state, so to speak. So you have to go through all this. So that is basically what people try to do. They have to, first of all, describe a task. Image processing, spell check, doing computing. You want to put it in a context so that you can store the information, represent the information as quantum state, go through the black box, create the environment so that the quantum evolution will follow certain, it's no definitive rule, but will follow the quantum mechanical rule to evolve, and then you get the output system, and then you do the measurement. Okay? So you hear all these names, so you have to have a suitable quantum system. You usually prepare the initial state. You want to represent as much information as possible and counter all possible possibilities in your calculation so that you can extract the useful piece. So they usually prepare the entangled state, put it in, and then let the thing evolve. So you apply all the electromagnetic field, whatever physics, physical realization platform needed to handle those quantum states, and then let it evolve and eventually do the measurement. So that is the simple quantum computing model in people's mind. Okay? Of course, after this page, everyone knows what's a quantum computer, right? But it doesn't matter, it is almost like a cartoon. Like this black box, that's roughly the idea. For mathematicians, excellent news. We don't need to worry so much. We can quickly go to what are the quantum computing problems that we might be able to help. You can clearly see that to make this thing successful, it requires the effort of many collaboration between computer science, they think about the algorithm, physicists, they would try to use all the theory of quantum mechanics to build the device, and then material science, how to engineer the thing, and chemists, because they need, sometimes the quantum effect will occur in certain particular molecules, then the chemists have come into help. And mathematics, using the Hilbert space model of quantum mechanics, you have to understand the theory behind before you even try to build something which might work, which will work. Okay? So let me quickly, using my background, bring you to the mathematical aspect framework of quantum mechanics, what we can do. So number one, very simple, you need to know something called density matrix, which is simply positive semi-definite matrices with trace 1. Here we always talk about complex Hermitian matrix. So everyone comfortable? So you have complex Hermitian matrix, which is positive semi-definite, which means that all the eigenvalues are non-negative. One way to see that is, and trace 1. Okay, so I don't care you use any photon, whatever quantum mechanical states, mathematically it is just density matrices. Okay? Step 2, you cannot just work with the object, your quantum state, but in the process you have to do communication, you need some quantum channel. In some computing process, you need some operation, including what we said earlier, that you apply electromagnetic field or whatever to the environment. So it is some kinds of quantum operation. It could be extremely complicated in the lab, depending on what kinds of tasks you want to achieve and what kinds of apparatus set up. But mathematically, it is extremely simple. So in 80s, or even before that, there were studies about what kinds of operation or channel will be realizable, even have the hope to be done by experiment to realize as a quantum operation or a quantum channel. So quantum state are represent all this fancy picture I showed earlier, matrices, and the map you want to transform is really very simple. It's just you input the quantum state, which is a matrix, and it is just a linear transformation of the form Fj, A, Fj star for R of them. Okay? So this is so important, I'll write it down. Along my talk about this. So typically you think about an n by n, a quantum state of n dimension. If it is a photon, it is 2 dimension. And then what you want to do is you want to transform it to something like that. You have finitely many matrix, and you want to have the outcome which is an m by m density matrix. So obviously you want a m by n matrix here, multiplied with the n by n, multiplied with the n by m. So you'll do the job. Of course, the arcs, the technique is how to select F1 up to Fr to fill the requirement, to change the environment, to produce a quantum state, or do the computation. Okay? So that is all you need. Density matrices and maps like this. And each individual piece is just F1A, F1 star. Okay? To make sure that density matrices go to density matrices, we require this condition. So if it is F1 is n by n, so you multiply in this way, then you get an n by n matrix. You apply this one. Okay, so at William and Mary, we do all this undergraduate research. Students say, oh, how many books I have to read before I start quantum information stuff?
What do an M and N means here?
Oh, so
Arbitrary?
the size of the matrix, but in quantum state, for example, photon is 2 by 2 matrix because there are only 2 measurable states. In some other system, you may have n different energy level. If you have 10 energy level, the quantum state corresponding will be a matrix in a 10 by 10 matrix. So it depends on the system. But we will actually combine several photons. We will not just use one photon to set up your quantum computer or your quantum computing environment. If you have 10 photons, you're talking about 2 to the power 10. Then in that case, the matrix will be 1024 by 1024. So it all depends on the quantum system, the platform. And transform a quantum state, you do not necessarily transform this system to the other system. Your impact may be from a 1024 system go to a 2048 system. So N and M will be different. So it allows all this flexibility. Right, so that is the setup. And my word to my students, don't worry, if you know what is density matrix, you have a little bit of linear algebra training, you know what is positive semi-definite matrix with trace one, and you also know the map, this one, and then you add them together, you're ready to go for quantum computing research. Okay, everyone ready? All right, so let's go. So let me give a name, Dn to be the set of n by n density matrix. One very basic question, which is useful and also natural in mathematics. You want to manipulate quantum state, right? Quantum computing, a major part of it or communication is to manipulate quantum state. The first question is that just like your elementary study, if I have some object, I want to use a transformation to transform it, what can I do? What kinds of quantum state can be transformed to other kinds of quantum state? In high school, your teacher tells you how to transform a number of real points, x1 up to xn to y1 up to yn, using a degree no more than n-1 degree polynomial. Same types of question, right? Can you use polynomial to transform real number to another set of real number? If you do complex analysis, you look at the Hartley space, the unit disk, you have n point in the complex unit disk, and then you want to transform it to another n point using homomorphic function. So it's very natural mathematically, and physically it also makes perfect sense. If I have n quantum state, can I even provide an environment or actually apply a quantum operation in channel to change it to n quantum state or k quantum state, A1, AK, go to E1 up to BK? Now, remember, all this fancy name of quantum operation, quantum channel, just represents such a map. So I'm really asking you, can you find F1 up to FR? Your discretion, how many R you want, 1,000, 2,000, of course, the smaller number intuitively is better. And can you do this job? You think that, oh, this is just matrix equation. These are known, right? A1 up to AK and B1 up to BK are known. The unknown are Fi. It's not a linear equation. It involves Fj, Ai, Fj star, but otherwise it is just a bunch of linear matrix equations. So immediately you can try, and I always encourage my student to try. Don't even listen to me. If you are given such a homework problem, what will you do? Or you use MATLAB, Mathematica, everything. Whatever you have learned in algebra analysis, you can try that. Okay? And then we can go back and see what are the kinds of results people are looking for, and then can we also match up to that kinds of requirement. Okay? So at this point, if you don't want to listen to me, find your way. At the end of the talk, tell me how you would solve this matrix equation. I would be happy to listen to and learn from you. Okay? But you can also see some of these sample results. What? Yes.
Maybe I'm just confused. You don't have to divide by R to get to the trace of one.
You require this, then that will guarantee trace preserving. Yeah.
Oh, some.
Right. So if different contexts, you have the right question. You look at the normalization, what people do. So here the normalization is here. Then you don't need to divide R. Okay. So first of all, we deal with a easy case and useless case. If you talk to quantum mechanics people, they will say, oh, Chi-Kwong, this is diagonal matrix. Diagonal matrix in those quantum states, they call classical state, classical phenomenon. So not very interesting. But to warm you up, let me talk about this A1 up to AK are all diagonal matrix, or I can make it fancy, say that this is a commuting family, AIAJ equal to AJAI, BIBJ to BJBI. So second course of linear algebra will tell you that those matrices you can find a unitary to simultaneously diagonalize them. Okay? And when you think about that, if I simultaneously multiply a U inside outside, it will not change. You can produce a map doing the diagonal matrix, and then you can produce a map that will do the general original matrix. Okay? So take my word for it. So now we can use the unitary similarity transform, basically looking at this question for transforming K diagonal matrix to K diagonal matrix of different size, could be. Okay? But remember, this is an easy case when I have diagonal matrix there, and I want to produce eventually the diagonal matrix. So this should be easier. And what actually happened is indeed quite easy. Easier than finding the abstract operator F1 up to Fr. We actually can reduce the problem to a very simple, relatively simple non-negative matrix equation problem as follows. It turns out that if you look at those diagonal, you can put it in a row. The second matrix, you have another set of eigenvalue. In the diagonal, you put it in this row. So you end up getting a K by N matrix. Likewise, you arrange B according to this order, you get a K by M matrix. All you need to do to solve this problem, instead of finding all this M by N matrix and so on and so forth, you only need to find a non-negative matrix D to make this equal. Then guarantee that you have a map of this form, transforming those diagonal matrix AI to BI. So it significantly reduces the dimension, the complexity of the problem. Okay? But don't forget, we do not only require such a form, we require this trace preserving condition. And in actually operator theory, we are also interested in so-called unit code, setting identity to identity, or trace preserving, like it will not change the trace of the matrix before and after, even though the size change, or both unitary and trace preserving, what we call three stochastic kinds of commutative positive map. So it turns out that it all depends on the requirement on D. Not only you get a non-negative matrix relating these two. Now, the eigenvalue of all these matrices are non-negative. So this is a non-negative matrix, and I want to find a non-negative matrix to make it work. Moreover, if I want unitary, I only need the matrix to be column stochastic. I want trace preserving, I need row stochastic. And if I want both, necessarily the dimension have to be the same, then I want a doubly stochastic matrix. Okay, so that is the kinds of result we are looking at. I posed the question of transforming this quantum state to this quantum state, eventually reduced to such a simple matrix equation problem. Now, you tell this to physicists, they will reject you immediately. Come on, Chi Kong, what is those Fi? That's what they need to do in their lab to produce the quantum operation. So in that case, we will tell them from D, actually, we can construct. Once we solve this equation, we can from D construct those F1 up to Fr. That will do the job. So that sort of complete the picture for this particular case.
So the problem is reduced to a linear program?
Yes, we reduce to a, yes, very good. So it is not completely solved, it reduced to a simple non-negative matrix equation or a linear programming problem, exactly. Yeah. And, okay, more question? I'm expecting more questions. Okay, if no, I will tell you the question in my mind later. But you are right on the spot, so it all reduced. So what kinds of, so I can say there exists, if only you can solve the matrix equation, it is nonsense, right? But I say that there exists a quantum operation, meaning that this is solvable, which can be reduced to a much more friendly checkable condition. And that is what I need. Okay? Moreover, once I check that condition, I can tell you how to construct F. Then I finish my job. So if you think about how to do these kinds of problem, that would be our target, our goal. Of course, eventually you still have to solve this equation, which may not be easy. Teacher, I don't know, I have not taught linear programming for many years, but I will tell students that even that is not entirely trivial, but luckily we have good numerical algorithm to do that. So if you really want to build a quantum computer to do experiment, of course, in the future, hopefully, the quantum computer will dominate, will do the job for us. But now, when we try to build this system, then we do all this and solve such a system, find a D to make it work. Conventional computing and all the theory, math theory we can use would be apply to it. Okay? And actually, I was expecting another question. How about the uniqueness? You saw this one, there will be more than one D you can use. And in fact, you will see later that for some reason, or first of all, after you get a solution, if there's no solution, end of story. If you get a solution, of course, we want a good solution, quote unquote. So later we will talk about what a good solution you want to get. So it never ends. So don't worry, you will not get out of job. I mean, even you solve this problem. And okay, so we will impose additional requirement from where? Of course, going back to the original problem, depending on what kinds of apparatus or what kinds of requirement the physicist friend told me, tell me that I have to do this and that, and I will deal with it. But at the moment, the solution depends on D. Okay, so with additional requirement, as I said already, I will deal with it later, tell you some natural question it will come up. And also, to do it, think about large size and so forth, we will require all the current non-active matrix equation theory and linear programming theory. And as I said, if you want additional conditions, this theory, you will have to refine it to see what kinds of solution will fit certain particular requirement. Okay? And if you are interested in pure mathematics, and it is sort of pure and also useful, some system is so large that it is basically infinite dimensional. So we can talk about infinite dimensional matrix, compact operator. So this result has also been extended to that direction. So completely positive map, quantum channel actually is a C-star algebra context. People discuss that. So there are all these operator theory direction if you are interested. Okay, so let me change gear, go back to another more realistic type. That was actually studied much earlier. So we have to deal with some special kinds of quantum state, which is usually manufactured. Sometimes with half-time people try to manufacture it to do experiment with pure state. So among all the density matrices, some are more special. Namely, those are rank 1 orthogonal projection, or simply positive semi-definite matrix of rank 1 and trace 1. So spectral decomposition or elementary matrix theory will tell you that such a matrix A can be written as X star, right? So remember, X is a long vector, and then X star will be a vector like that. So this rank 1, if it is trace 1, then X must be a unit vector. So those are what they call the pure states. Okay. So how about changing a bunch of pure state to a bunch of pure state? That is more realistic problem. Actually, studied much earlier, and we have some later proof covering that. So we attach our paper to it. So same question: can I have A1 up to AK? Now it's not diagonal, but pure state. Change pure state to pure state. Same old question. Solve this equation, but this happens if and only if the equation is solvable. It's not an acceptable answer. So what happened? It turns out that also we can do it in a very, very efficient way in checking something. Not immediately tell you the solution, but reduce it to such a simple system. So you may, again in matrix theory, you may know that this is what we call a Gram matrix. So if we have a K vector, a unit vector forming the pure state xi star, and then y1 up to yk, yi star. So we want this to happen. It turns out that we can flip the thing around. Notice that xi star xj is a number, right? So all this is a k by k matrix. You just list all the x1 and multiply x1 up to xk to get your xij matrix, the Gram matrix, which will be k by k. And I don't care about the original dimension. If you have k state, I just get a k by k matrix. Do the same thing for y, you get such a matrix. It turns out that this could happen if and only if you can find a positive semi-definite matrix C, so that the entry-wise product of C can produce X, the Gram matrix of X. Much simpler than before. Right? A large dimension problem, abstract problem, reduced to such a simple, sure product problem. Okay? Of course, I have to satisfy my physicist friend saying that once I know C, I change the problem completely to something else. But when I solve this question, after I solve this question, I can always produce F1 up to FR for you.
So now it's an SDP.
Okay, semi-definite programming come up. Yes, indeed, it will come up. So first of all, let me talk about simple thing, and then I will get to SDP. Very good. So first of all, notice that in statistics, right? Statistics department, xi star xj all are unit vector. So what do we call this? Is this is a correlation matrix, right? This is another correlation matrix. You want to have an entry-wise PSD matrix multiply this correlation matrix to get this correlation matrix. C must be correlation matrix. The 1, entry is 1 on both sides, so C11 can only be 1, right? Remember, it's the entry-wise product. Just think about that, right? So you want your C, 1, C1, 2, C2, 1, C2, 2. Think about the 2 by 2 case. When you entry-wise multiply Y1 star Y1, which is 1, which is a 1, equal to something 1, 1. No choice. C1 must be 1, right? And not only the diagonal entry, we are in very lucky situation. If every single yi star yj is not 0, then you can simply do this exercise by this guy divided by this guy, right? This guy divided by this guy. Then you can tell what is the C11, C12, C13, and so forth. True? So you really hope that happens. Of course, generic in matrix theory, we say that that is the case. So yij, if none of them are 0, then the only choice for C is this one. Then the problem reduced to check this particular construction of C. There are only 2 possibilities. It is positive semi-definite or it is not. If yes, I have the quantum channel. If no, I don't. So that is the lucky happy case. Okay? Another case is that, okay, suppose you have yi star yj, which is 0, something 0 here. But you have a non-zero guy here. Again, I'm very happy because I can tell my physics friend say that, oh, you cannot have a number multiply 0, get a non-zero number, which means that no such quantum channel, right? So these 2 cases are easy. So the most challenging case, of course, is that suppose I see a 0 here. So let me enlarge that. So you have 1, 1, 1 here. Okay, you have a 0 here, and you also have a 0 here. So the big question is that, how do I assign this value so that I have a number times 0 into 0, and yet the resulting matrix is positive semi-definite? You think that, oh, I simply put 0 there. Usually it does not work. You may need to put some non-zero thing here so that this has the positive semi-definite structure. So it's interesting, this world, when you have no choice, you just check C. When you have choices, it makes it difficult. What choices of C13 would allow me to get a positive semi-definite matrix? So you actually would survey all the entry. Whenever yi star yj are non-zero, you are good. You know what is Cij. 1, 0, 1, non-zero, again, you are good. There's no such operation. But when all the pattern agree, 0 go with 0, then you have a lot of question mark. You have to fill in what entry to put there to get a positive semi-definite matrix. Have you seen this kind of problem?
Yes.
Compression problem, very good. So in matrix theory, it is known as the compression problem. Very tough. If some particular band pattern or some graph pattern, caudal graph pattern, yes, that can be solved. In general, it could be difficult. And semi-definite programming. Thank you for mentioning that earlier. So eventually, when the theory hit the wall, you can only do so much. At that point, you either use the theory to solve your problem. If not, then use positive semi-definite programming to check whether such a compression problem is solvable.
So, semi-definite programming is definitely harder than linear programming.
Yes.
So why would you not use your linear programming?
Because this is a different problem, right? The first one is diagonal matrix, diagonal state. Now I'm talking about pure state. Remember, I'm already telling you 2 different results. The first one is about diagonal matrix.
So it may not be a commuting family.
May not be.
Okay, I see.
If it is commuting in rank 1, then I'm extremely happy. I can use pencil and paper to tell you the answer. Good remark, because we are going to go to general quantum state. We are only doing 2 special cases. One is the commuting situation, which is the classical state. The other one is the pure state. Right. And then we do this one. Okay. Then, of course, to publish the paper, we have the general theorem. That is why I attached this paper to the earlier result, saying that we also have some contribution. Because we do have a result for general state. And you can imagine, exactly as you point out, commuting family, you have this simple linear programming trick to check it. And then for pure state, you need this semi-definite programming thing to resolve the problem. And general thing, we use all the special theory to give a good canonical form for those AI. and give a good canonical form BI and say that this is solvable if and only if a bunch of equations is solvable. Don't even try to examine it in detail. It is complete nonsense. It's a step further, saying that better than saying that this equation is solvable. I just make it reduce the number of variables as the minimum number. And I can still use definite programming and so forth, but this is totally useless. My friend Choi, who is a pioneer in this PVC female channel, saying that this is what we call abstract nonsense. This happened if and only if that happened. That thing is almost impossible. So there is something situation like that. The only good thing is that you can use this to deduce some special case, like the early result, pure state to pure state. You can also say something clever about pure state to general state, or general state to pure state. Publish a paper, so that is about the value of this result. So obviously, it cries for, is there a better way to do that? In the future, no matter how small the quantum computing model computer we want to check to build, we want to solve some problem. Can I convert K quantum state to K quantum state? Semi-definite programming, yes, but quickly you hit the wall. Moderate size problem, it just hung there, cannot help solve the problem. Yes?
So you're saying the previous condition, more general condition you had
Right.
was actually a semi-definite program.
You can also formulate
Okay, I see.
positive semi-definite programming. It's extremely useful because in quantum information science, many problems are just density matrix, positive semi-definite matrix. Construct something is also related to the positivity. So this is an extremely powerful tool to do that. Right? But unfortunately, the size easily get out of hand. I'm not even talking about practical problem. As I said, practical is not practical, it's preparing your quantum computing research. So always you only talk about, I don't know, 32 by 32 matrix, 20 of them, 50 of them. But that is bad enough for the semi-definite program. Okay? So even for moderate size problem, it has a problem. So we have to switch it. So in 2014, actually, when I visited IQC 2-3 years ago, I worked with the optimization group there, and Henry Walker is the leader of the group who semi-definite programming, compression program have a lot of contribution. So he suggested we can try this projection method. Maybe some of you in optimization have seen that. Very simple. It ripped back from von Neumann's intersection of subspace. Everything. So what he do is the following, or people extend it to the following. If you have two convex sets, you can do the following alternating projection algorithm. You pick a point in one set, project it in the second set using the least square, for example, project it to the other one, project it to the other one, and do it multiple times, and guarantee convergence if you start with convex set. And you will always see a point in the intersection if there's intersection. What if there's no intersection? Then you still get convergence sequence in each of the set. X will converge to the point X star, Y will converge to the point Y star. And these 2 points will be the 2 points with nearest distance between the two convex sets. Convergent, very nice, everything is good. Okay, so how do we make use of that in our problem? So let us look at the setup. So here is a secret weapon I have not told you, but still very matrix theoretic and easy to understand. Construct a quantum operation is constructing all this F1 up to FR, satisfying this condition, and we want it to fulfill certain particular task. Usually it's too abstract, too difficult, so our